Hi everyone, I'm Lap-Loi Chung from the National Center for Research on Earthquake Engineering and from the Departments of Civil Engineering, National Taiwan University and National Chung University. This is my name in Chinese, Zhong Li Lai. Welcome to the course Seismic Evaluation and Retrofit of Structures, Lecture 4-2, over at the Department of Construction Engineering, National Taiwan University of Science and Technology. This is the lecture on Simplified Detail Evaluation 2. In detail evaluation, we have to know about the material strength of the structure and also the size reinforcement of those structural members. And this is simplified detail evaluation. Simplified means that it can be handled, it can be conducted by hand calculation. And today we'll concentrate on seismic capacity of a structure with an example to illustrate how to conduct simplified detail evaluation in order to get the seismic capacity of a building. And here's some terminology. And in order to find out the seismic capacity of a building, VBS equal to summation. J equal to from J equal to 1 to NC. NC is the number of column lines. Beta J VCJ. And VCJ is the lateral strength of a column. And beta J is the reduction factor of the column depending on the failure mode. In order to find out the lateral strength of a building, we have to know about the flexural strength and shear strength of the column. And flexural strength and shear strength of a column depends on the actual design actual force of the column. And actual design force comes from the dead load and live load of the structure. Dead load of the structure, in Chinese, 静载重, is the loading includes the weight of the members and also anything attached to the structure or anything that moves in phase with the structure. Live load in Chinese, 活载重. And live load is movable from the structure. During earthquake, there may be some relative displacement between the live load and the structure. And that load includes the weight of parapet wall. Parapet wall, here's a picture. That's the low wall, is not high wall at the edge of the roof or the floor. This is parapet wall, and this is also parapet wall. And roof tile is the tile on the roof, in Chinese 屋瓦. And parapet wall in Chinese 女儿墙. And slab is the floor, and in Chinese 楼板. Partition wall in Chinese 隔间墙. From the dead load and live load of the structure, then we can calculate the actual force of a column, and in Chinese 轴力. And after considering the failure mode, including flexural failure mode and shear failure mode, flexural failure in Chinese 劳去破坏, shear failure in Chinese 剪力破坏. After considering all failure modes, then pick up the minimum one, then we can have the lateral strength of a column line. And here's an example to illustrate how to have the seismic capacity of a building by using simplified detail evaluation. This is a building at Reipu Elementary School. That's the front view of the building. That's the rear view of the building. And this is the plan of the building. And there are totally 7 C1 columns with size 35 by 40 centimeters, and 3 partition columns with size 24 by 40 centimeters. And Fc prime is the compressive strength of the building, and Fy is the yielding strength of the longitudinal reinforcement. Fyt is the yielding strength of the transverse reinforcement. Please notice that the compressive strength of the core of the building is very low as 113 kgf per cm square. This is the elevation of the building, and here's the reinforcement of the C1 column. That's the column of classroom, and this is for C2 column. That's the column for the partition. That's the column of partition walls embedded in the partition walls. There's the reinforcement of B1 beam, RB1 beam, and WB2 beam. Okay, in order to find out the design actual force of a column, we have to know about the dead load of the structure, including the dead load of the roof and the dead load of the second floor. And the dead load of the roof includes the weight of parapet walls equal to unit weight 2.4 ton force per cubic meter, and the length equal to 18.98 meter, and the thickness of the wall is 12 centimeters, and the height of the wall is 60 centimeters, and it makes to 3.28 ton force. And the roof of the tiles, the unit weight is 0.03 ton force per meter square, and the length of the roof 18.98 meter, the width of the roof 11.51 meter, and it makes 6.55 ton force. And the weight of the slab, that's the weight of the roof slab, equal to unit weight 2.4 ton force per cubic meter times the length 18.98 meter. The width of the slab 11.51 meter. The thickness of the slab 14 centimeters. That's 0.14 meter, equal to 73.40 ton force. And the weight of the columns C1 and C2 equal to unit weight 2.4 ton force per cubic meter, and the dimension, the depth of the column C1 0.35 meter, and the width of column C1 0.4 meter, and the height 1.8 meter. Only half of the height is lumped to the roof. Therefore, the height of the column is 1.8. There's 3.2 meter divided by 2. And the total number of column C1 is 14, equal to 8.47 ton force. 2.4 ton force per cubic meter. 0.24 meter is the depth of column C2, and 0.4 meter is the width of column C2. 1.8 is the half of the height of column C2, and 3 is the number of column C2. It makes 1.24 ton force. And the weight of beams WB2, unit weight 2.4 ton force per cubic meter, total length 33.76 meter, and the width 0.4 meter, depth 0.4 meter, equal to 12.96 ton force. And the weight of beams RB1, unit weight 2.4 ton force per cubic meter, total length 29.4 meter, width 0.24 meter, and depth 0.35 meter, and it makes 5.93 ton force. And the weight of beam B1, unit weight 2.4 ton force per cubic meter, total length 40.8, and the width 0.35 meter, and the depth is 0.6 meter, equal to 20.56 ton force. And the weight of partition walls, unit weight 2.0 ton force per cubic meter, and the length 6.9 meter, and the thickness 0.24 meter, and the height 1.45. This is the half of the height of the partition wall, and the number of partition walls equal to 3. Therefore, it makes 14.41 ton force. The floor area of the roof equal to 205 meters square, and the dead load of the roof, and we sum all them up, then we have 146.8 ton force. Therefore, the dead load, the unit dead load of the roof, that's the dead load of the roof per unit floor, equal to W roof divided by A roof, equal to 0.716 ton force per meter square. And by comparing with preliminary evaluation, the unit dead load of the roof equal to 0.750 ton force per meter square. Therefore, preliminary evaluation is a little bit overestimate the dead load, the unit dead load of the roof. And the live load of the roof equal to 250 kgf per meter square. That's a 0.25 ton force per meter square. And under earthquake, there may not be 100% live load. There may be only 50% or half of the dead load. Therefore, dead load plus 1/2 live load in order to calculate the actual force, the design actual force of a column of the roof. The dead load and plus 1/2 live load of the roof per unit floor area. W, small w roof equal to capital W roof divided by capital A roof plus 0.25 divided by 2, only half of the live load equal to 0.841 ton force per meter square. And the floor, similarly, the floor area of the second floor equal to 205 square meter. By a similar procedure, we can have the dead load of the second floor, W2 equal to 169.7 ton force. And the dead load, the unit dead load of the second floor equal to W2 divided by AF2 equal to 0.828 ton force per meter square. And then if we consider preliminary evaluation, W2 divided by AF2, that is the unit dead load of the second floor, equal to 0.9 ton force per meter square. Therefore, the preliminary evaluation is a little bit overestimate the dead load of the second floor. With the dead load of the roof and also the dead load of the second floor, then we can have the total dead load of the structure. W equal to W roof plus W2 equal to 316.5 ton force. And from previous lecture, in preliminary evaluation, we have the dead load of the structure equal to 38.25 ton force. Therefore, preliminary evaluation is a little bit overestimate the total dead load of the structure. And the live load of the second floor equal to 250 kgf per meter square. That is 0.25 ton force per meter square. And under earthquake, there may be only 50% of the dead load. Therefore, we use dead load plus 1/2 live load of the second floor to calculate the design actual force of the column. Therefore, the dead load plus 1/2 live load of the second floor per unit floor area, small W2, equal to capital W2 divided by AF2 plus 0.25 divided by 2 equal to 0.953 ton force per meter square. So far we have the total dead load plus 1/2 live load of the structure. Now we move to the calculation of the design actual force of the column. And we take C1, number 1 column, as an example. Therefore, C1, second floor, on the second floor, for number 1 and number 7. And the area responsible for C1, covered by C1, equal to 0.038 of the total floor area. Therefore, the actual load, the design actual load of C1 on the second floor for number 1 and number 7 equal to 0.038 small w roof times capital A roof equal to 0.0384 times 0.841 times 205 equal to 6.62 ton-force. Therefore, the actual load of C1 on the second floor for number 1 and number 7 is 6.62 ton-force. With similar procedures, we have the actual load for C1 on the second floor, number 1 and number 7, 6.62 ton-force. For number 2, 3, 5, 6, the design actual force is 18.19 ton-force. For number 4, is 13.28 ton-force. For numbers 8 and 14, the design actual force is 2.59 ton-force. And for number 9, 10, 12, and 13, the design actual load, the design actual force is 10.55 ton-force. For number 11, the actual load is 5.17 ton-force. Then we move to the column of partition walls. C2 on the second floor for number 1 and number 3 equal to 5.17 ton-force. For number 2, the design actual force is 10.34 ton-force. Then we sum up all the design actual force on the second floor. There's columns of classroom C1 from number 1 to number 14, and the actual force varies from 6.62 ton-force to 2.59 ton-force. And also for the columns of partition walls, C2 for number 1, 2, 3, and it varies from 5.17 ton-force to 10.34 ton-force. Similarly, for the column on the first floor, we can have the design actual force NU, and we take C1 column as an example for number 1 and number 7, and it counts for 0.038 AF2. That means that the total floor area is AF2, and the column C1, number 1 here, is covered by the area 0.0384 of the total area. Therefore, C1 on the first floor for number 1 and number 7 equal to 0.0384 small w2 times AF2. And you have to keep in mind that the actual load on the second floor is accumulated. The actual load on the second floor is accumulated to the first floor. Therefore, C1 1F 17 equal to C1 2F, the second floor, 17 plus 0.0384 small w2 times AF2 equal to 14.12 ton-force. With similar procedure, we can have the actual load, the design actual force for column C1 number 2, 3, 5, 6 on the first floor equal to 38.80 ton-force. For number 4, 28.32 ton-force. For number 8 and 14 equal to 5.52 ton-force. For number 9, 10, 12, and 13, the design actual force is 22.51 ton-force. For number 11, the design actual force is 11.03 ton-force. For the columns of partition walls, number 1 and 3, is 11.03 ton force. For number 2, the design actual force is 22.06 ton force. And all the column design actual force is summed up in this table. And the first table is for columns of classroom C1 from number 1 to number 14. And this is the actual load. It varies from 14.12 ton force to 5.52 ton force. And the second table sum up the design actual force of the columns or partition on the first floor C2 from number 1 to number 3, and it varies from 11.03 ton force to 22.06 ton force. In order to calculate the lateral load strength of a column line, we have to know about the vertical distribution of the seismic force. And under the assumption that the vertical distribution of the seismic force for the whole building is the same as for a column line. And alpha 3 is the vertical distribution of the seismic force to the roof, equal to W3H3 divided by W2H2 plus W3H3 equal to 0.634. And for the second floor, the vertical distribution of the seismic force for the second floor, alpha 2, equal to W2H2 divided by W2H2 plus W3H3 equal to 0.364. And W3 equal to 146.8 ton force, W2 equal to 169.7 ton force, and H3 is the elevation of the roof equal to 7.2 meter, and H2 is the elevation of the second floor equal to 3.6 meter. And we are going to find out the lateral load strength of column line C1, number 1. That's the column here. That's the column here. And we have the actual force, design actual force on the second floor, the design actual force on the first floor. And from the reinforcement of the column C1, we can calculate the flexural strength, the moment strength of the column on the second floor, 10.4 ton force meter. On the first floor, the moment strength is 11.32 ton force meter. We can also calculate the moment strength of the beam WB2 with the reinforcement here, the positive moment. The positive moment strength equal to 6.73 ton force meter. The negative moment strength equal to 7.75 ton force meter. Then we consider all possible failure modes. The first one is the first floor column shear failure. V1 equal to Vn. Vn is the shear strength of the column, equal to Vc plus Vs, equal to 17.00 ton force. The second failure mode is the flexural failure on the first floor column. V2 equal to 2 times MC1. MC1 is the moment strength of the column on the first floor, divided by HC1. HC1 is the clear height of the column, equal to 2 times 11.32. And the height of the floor is 3.6, and then minus the depth of the beam. Therefore, the clear height of the column equal to 3.6 minus 0.4, and the lateral strength under this failure mode equal to 7.07 ton force. So far, we have the lateral strength of the column line under failure mode 1 equal to 17.00 ton force. Under second failure mode equal to 7.07 ton force. And we move on to the third failure mode. That's the failure mode with second floor beam flexural failure. And V3 equal to MC1 plus MC2 plus MB2L. MB2L is the moment strength of the beam on the second floor plus MB2R divided by alpha 2H2 plus alpha 3H3 equal to 4.84 ton force. So far we have V1, V2, V3 for failure modes 1, 2, and 3. And we move to the last failure mode. That's the beam flexural failure on the second floor and the roof. V4 equal to MC1 plus MB2L plus MB2R plus MB3L plus MB3R divided by alpha 2H2 plus alpha 3H3 equal to 4.21. So far we have the V1 for failure mode 1, V2 for failure mode 2, V3 for failure mode 3, and V4 for failure mode 4. Then we pick up the least one, the smallest one. That is the lateral strength of the column line C1, number 1, equal to 4.21 ton force. The failure mode with the least lateral strength is the control failure mode. That's the failure mode to be realized. Then we move to column line C1 for number 2, 3, 5, 6. 2, 3, 5, 6. Then we have from the material strength and the reinforcement of the column. We can have the moment strength on the second floor equal to 11.04 ton force meter. The moment strength on the first floor equal to 13.66 ton force per meter. We can also have the positive moment strength of the beam and negative moment strength of the beam equal to 6.73 and 7.75 respectively. From the information of the moment strength and shear strength of the column and also the moment strength of the beam, then we can find out the lateral strength under different failure modes. The first failure mode is shear failure on the first floor column. V1 equal to Vn equal to Vc plus Vs equal to 21.33 ton force. The second failure mode is the flexural failure mode of the first floor column. V2 equal to 2 times MC1 divided by HC1. HC1 is the clear height of the column equal to the floor height 3.6 minus the depth of the beam 0.4 and the moment strength of the column equal to 13.66. Therefore, V2, the lateral strength under failure mode 2, equal to 8.54 ton force. So far we have V1 for failure mode 1, V2 for failure mode 2. Then we move to failure mode 3. That's the flexural failure on the second floor beam. V3 equal to MC1 plus MC2 plus MB2L plus MB2R divided by alpha 2H2 plus alpha 3H3 equal to 6.66 ton force. So far we have V1, V2, V3 for failure modes 1, 2, and 3. Then we move to the last failure mode, that's the flexural failure of the beams on the second floor and the roof. V4 equal to MC1 plus MB2L plus MB2R plus MB3L plus MB3R divided by alpha 2H2 plus alpha 3H3 equal to 7.25 ton force. Once we have V1, V2, V4, V3, and V4 for all failure modes, then we pick up the minimum one. That's the failure mode to be realized, and it is the lateral strength of the column line C1 for number 2, 3, 5, and 6 equal to 6.66. That's the failure mode 3. Therefore, the lateral strength of column line C1 for number 2, 3, 5, and 6 equal to 6.66 ton-force. Then we move to the column of partition C2 for number 1, 2, and 3. And here's some information about the column, the design actual force on the second floor, on the first floor, and from the reinforcement and actual load of the column, we can calculate the moment strength of the column on the second floor equal to 4.496 ton-force meter. On the first floor equal to 4.736 ton-force meter. Then considering the first failure mode, that's the shear failure on the first floor on the column, the shear failure of the column on the first floor, V1 equal to 10.82 ton-force. Then we move to the failure mode, the second failure mode, V2 equal to 2 times MC1 divided by HC1 equal to 2 times 4.736 divided by 3.6 minus 0.4 equal to 2.96 ton-force. So far we have V1 and V2 for failure mode 1 and failure mode 2. We move to the third failure mode, that's the fractal failure, of the beam on the second floor. V3 equal to MC1 plus MC2 plus MB2L plus MB2R divided by alpha 2H2 plus alpha 3H3 equal to 1.57 ton-force. Then we move to the last failure mode, that's the fractal failure of the beams on the second floor and the roof. V4 equal to MC1 plus MB2L plus MB2R plus MB3L plus MB3R divided by alpha 2H2 plus alpha 3H3 equal to 0.805 ton-force. Once we have the lateral strength under failure mode 1, 2, 3, and 4, pick up the minimum one, that's the failure mode to be realized. Therefore, we can have the lateral strength of column line C2 for number 1, 2, and 3 equal to 0.805 ton-force. And here's the table to sum up the lateral strength of all column lines of classroom. C1 from number 1 to number 14. And the lateral strength varies from 4.21 ton-force to 4.37 ton-force. And the failure mode, all of them are beam failure. Maybe the flexural beam flexural failure on the second floor or on the roof. And here's the table for the lateral strength of the column lines of partition. C2 from number 1 to number 3. And the lateral strength equal to 0.807 or 0.828 for number 2. And the failure mode is column failure, but not on the first floor, but on the second floor. Therefore, the ultimate base shear strength of the building, VBS, the seismic capacity of the building, equal to summation from J equal to 1 to NC, beta J times VCJ. VCJ is the lateral strength of column line J, and beta J is the corresponding reduction factor for column J. Because no failure mode on the first floor, therefore the reduction factor of all column line equal to 0.97. Therefore VBS equal to 0.97 times 84.068 equal to 79.865 ton-force. That's the seismic capacity of the building. is the ultimate base shear strength of the building. And by simplified detail evaluation, we have VBS equal to 79.865 ton force. And by preliminary evaluation for the same building, VBS equal to 140.8 ton force. Therefore, preliminary evaluation overestimates the seismic capacity of the building. There are two reasons. One is that the compressive strength of the concrete is so low as FC prime equal to 13 kg per centimeter square, and the average compressive strength of the school building is about 160 to 180 kgf per cm square. And for this particular building, the compressive strength of the concrete is extraordinarily low. Therefore, we have very low seismic capacity for this building. Another reason is that in order to simplify the calculation, we neglect the window shields. Therefore, all columns are long columns. Column with relatively larger height. Therefore, the lateral strength may be smaller. If the lower part of the column is confined by window shield, the clear height of the column will be smaller. Therefore, the lateral strength will be higher. But in this case, we neglect all the window shields, so that the clear height of this column will be higher, and the lateral strength may be lower. That's the reason why the seismic capacity calculated from simplified detail evaluation is much lower than the preliminary evaluation. And here are some references for this lecture. The first one is Seismic Design Code of Buildings, published in 2011 by the Ministry of Interior. The second one is a Structural Concrete Design Code, published in 2011, also by the Ministry of Interior. And this is the videos for Lecture 2. This one, Lecture 4-2, Simplified Detail Evaluation 2, is under construction, and it will be uploaded to YouTube later. And this is video for Lecture 3, Lecture 2, and Lecture 1. And in this lecture, we use an example to illustrate how to calculate the seismic capacity by simplified detail evaluation. In order to find out the lateral strength of column line, we have to know about the design actual force of column NU, and from the design actual force of column, we can calculate the flexural strength and shear strength of the column, and also the shear strength of the beam, because flexural strength and shear strength of a column depends on the design actual force of the column. Then we consider all possible failure modes. From each failure mode, we can have the lateral strength of the column line, Vk, and from lateral strength under all failure modes, we pick up the minimum one. That's the failure mode to be realized, and the minimum one is assigned to be the lateral strength of the column line. And according to the failure mode, we can have the reduction factor for the lateral strength of the column line beta J. Once we have the lateral strength of all column lines and the corresponding reduction factor, then we can have the ultimate base shear strength of the structure, VBS, equal to summation from J equal to 1 to NC beta J times VCJ, and that is the seismic capacity by using simplified detail evaluation. That's all for this lecture, and the video will be uploaded in this channel. Thank you. See you next time. Bye bye.